Yo! Welcome to the second edition of Topic 4 Waves. Within this topic, we're going to be talking about 4.2 Traveling Waves. What everyone is most familiar with when they think of waves is water waves, such as the ones you can see on a beach. However, waves can come in many different forms and sizes, and when most commonly referring to waves, we refer to an oscillation of matter, where energy is being transferred. This characteristic we'll get on in later. So, when talking about mechanical waves, then we could talk about waves such as sound waves, oscillating masses, water waves, and other types of waves. A necessary condition for mechanical waves is that they would need a medium in which they would travel through. To define a medium, we can say that it's a substance that makes it possible for the transfer of energy from one location to another location to occur. Examples of mediums could be air, water, or other substances in which waves can travel through. A key characteristic to waves is that they have the ability to transfer energy from one place to the other without actually transferring matter. Waves that continuously transfer energy away from a source are known as continuous traveling waves, or also referred to as progressive waves. There are two main types of waves that we'll be covering in traveling waves. This includes transverse waves and longitudinal waves. First, we're talking about a transverse wave. In a transverse wave, each part of the medium oscillates perpendicularly to the direction in which the wave is transferring or propagating energy. Examples of transverse waves in the real life are water waves, light waves, a Mexican wave in a sports stadium that's oscillating up and down while perpendicularly to the direction it's propagating energy, vibration on guitar strings, and what is visible in front of you, a transverse wave on a rope in which the waves are moved up and down and the movement of energy is to the right, so it's perpendicular to the movement up and down. Transverse waves can be displayed on the following graph as follows on a displacement, which is x, distance graph. So, when talking about a transverse wave, each part of the medium oscillates perpendicularly to the direction in which the wave is transferring energy, which is to the right. Transverse waves have two characteristics to them, unlike that do not follow with longitudinal waves. They have crests and troughs. The crest is the top part of a transverse wave, which I'm going to be labeling as C. It's the highest point, or x naught. We can also say x naught because this is also denoted as our amplitude. And then we have a trough, which is the lowest point. And this is going to be the negative x naught, which is going to be the lowest point or our trough. Successive crests and successive troughs are in phase. And if you want to determine the wavelength of one of these waves, since this is a displacement distance graph, we can say that the wavelength, lambda, is the distance between 2 points that are in phase, which is a crest to crest, or from here, from trough to trough. If you were to measure this distance, you would get what the wavelength is of your transverse wave. This transverse wave can be shown in a simulation as follows. This is an example of a wave on a string, in which each part of the medium is oscillating perpendicularly. As you can see, it's moving up and down each part of the medium, in which the wave is transferring or propagating energy, which would be towards the right. We can find if I pause it at this moment, we can indicate where the crests are and the troughs. The crest is the top point, and the bottom part of the wave is the trough. If we want to measure this exact distance, we can take our crest, take our ruler and place it, and we can find the next successive crest, which is here. This distance is 4.2 centimeters, and that is the wavelength of this wave. Another important thing to state from here is that the particles, as you can see, are moving up and down, and that means that they're vibrating up and down. Next, we have longitudinal waves. In a longitudinal wave, each part of the medium oscillates parallel to the direction in which the wave is traveling, or the direction of energy propagation. Examples of longitudinal waves include sound waves, earthquakes, ultrasound waves, and once again, what is visible in front of you, a slinky or a spring. When thinking about a longitudinal wave, you can think of a slinky. If you were to push a slinky back and forth, you'd be creating a longitudinal wave. We said that each part of the medium oscillates parallel to the direction in which the wave is traveling. As we can see, this is an example of a spring, or we can relate it to a slinky, in which the movement is towards the right, and it is also propagating energy to the right, so the movement of the oscillations is parallel to the direction it's traveling energy in. Unlike with transverse wave, which has crests and troughs, longitudinal waves have a series of refractions and compressions. A compression can be, I will say that this is C. Compression is called the regions of high pressures and where the particles are close together, such as here. This would be the center of a compression. Another center of a compression would be over here, where the particles are close together and where the slinky is condensed. Then we also have something called refractions, which I'm going to label as R. Refractions are where the particles are furthest from each other and when there's the least amount of pressure. Now, just like with transverse waves, if we want to measure the distance of a wave, the wavelength, we can just measure the distance between successive crests or wavelengths, or refractions, So, this distance between a compression and a compression would be equal to the wavelength, and then this distance between the refraction and the refraction would also be the wavelength of the wave. In order to better demonstrate a longitudinal wave, we can display it through another simulation. In this simulation, this is a sound wave, and as previously stated, sound waves are longitudinal waves. Within the sound waves, we can visually see where the refractions and the compression of the waves are. If I were to pause at any instant in time, we can see that the particles here are more bunched up on this area, more bunched up over here, here, and here they're further spread apart. So we can say that where the particles are close together, with this high pressure, these are the compressions. The areas in between, where there's not many particles and where they're far apart, are refractions. This can be shown on the waves. As you can see here, the center of a white area would be the compressions, and the center of the darker areas would be the refractions. If we wanted to know the wavelength of this wave, we'd have to take the distance from the center here of the compression to the center of a compression, or the center of the refraction to the center of a refraction. Next, we'd like to touch upon wavelength, as a key characteristic that both transverse waves and longitudinal waves have. The wavelength of a wave can be defined as the shortest distance between 2 points on a wave that are in phase. The wavelengths of a transverse wave can be measured as the shortest distance between 2 crests or troughs. With longitudinal wave, this can be measured by the shortest distance between 2 compressions or refractions. The symbol that denotes the wavelength is lambda, and the unit that it's usually in is meters. If this is a different unit, then usually we like to convert it to meters. When thinking of speed, the formula speed is equal to distance over time instantly pops in our head. This also relates to the speed of a wave, or wave speed, denoted by the symbol c. This can be defined as the distance a wave has traveled in a given time. The equation that is used to find the speed of a wave is c is equal to frequency times by lambda, or wavelength. The unit of speed of a wave is in meters per second -1. We can also rewrite the wave speed formula as wavelength divided by time period, because in 4.1 oscillations we stated that frequency is equal to 1 over capital T, 1 over the period of a wave. The equation C is equal to frequency times wavelength is given in your IB data booklet. Another thing to note when talking about wave speed is that once a wave has been created, the frequency cannot change. So if the wave changes, this is due to the wave entering a new medium, in which there would be a corresponding change in the wavelength. When previously talking about transverse waves, it was mentioned that an example of a transverse wave is a light wave. Light waves travel in waves, and we humans can see a whole spectrum of light, such as visible to you on the screen, as you can see, from red to purple. All these different colors on the spectrum have differing wavelengths, with red light having the longest wavelength, as visible, of 750 nanometers, and purple having the shortest of 380 nanometers. However, when looking upon it, the visible light spectrum is only a tiny fraction of a much bigger spectrum known as the electromagnetic spectrum. These waves are all around us, and they're widely regarded as light because they're waves that we humans can detect with our eyes. These all exhibit similar characteristics, while the only difference being between them is their wavelengths respectively. As you can see, that going from radio waves to gamma rays, there's decreasing wavelength, as radio waves have the largest wavelength and gamma rays and cosmic rays having the shortest wavelength. However, there is increasing energy. There is a similar characteristic upon all these waves, as light travels all at the same speed. Light travels at a speed of 3.0 times 10 to the 8th power meters per second, and this is for all of the electromagnetic spectrum. Finally, we'd like to touch base upon sound waves. Sound waves are examples of longitudinal waves, as previously stated, in which each part of the medium oscillates parallel to the direction in which wave is propagating energy. Sound waves all create a series of compressions and refractions, and all waves have a specific frequency, but there are frequencies of sound that we humans can hear. These frequencies are defined as within the audible range, and this is a range of frequencies that we as humans can hear. This range lies somewhere between 20 Hz and 20 kHz. Anything beyond or below this range is inaudible, and anything beyond this range is classified as an ultrasonic. The speed of sound, just like electromagnetic waves, has a specific speed. The electromagnetic spectrum and all had a speed of 3.0 times 10 to the 8th power meters per second. Speed of sound, however, is approximately 343 meters per second. This value can actually be experimentally determined. Since we know that speed is equal to distance over time, we can approximate the speed of sound to be by measuring the time it takes for a certain sound to travel a certain distance, and this is a very fun experiment to do on your own. Next, we'd like to go through some IB Paper 1 questions for SL students first, and then an HL student one. So pause the video maybe, and I'll read over the question. Which of the following correctly relates the direction of oscillation of the particles in a medium to the direction of energy propagation for transverse and longitudinal waves? I hope the answer you chose was B, because in a transverse wave, the particles travel perpendicularly to which in the direction that the wave is traveling energy. In a longitudinal wave, the particles are moving parallel to the direction of energy propagation. So the answer would be B. Next, this is an IB paper question for HL students. A longitudinal wave propagates along a spring. This shows the position of the beads at a particular instant. Here we're dealing with longitudinal waves because we can see that it creates a series of rarefactions here and compressions. So which of the following is the best estimate of the wavelength? We previously touched base upon that the wavelength is also equal to the distance between the center of the rarefactions or the center of the compressions, or just at any points that are in phase with each other. If we know that one box is 1 centimeter, we can measure the distance from, say, here, which is the center of a compression, to here, which is the center of another compression. If you were to count these boxes, you'd get 8 boxes, which is equal to 8 centimeters, your answer being C, 8 centimeters. Finally, I would like to go through a paper 2 style question. So, part A asks, what is the amplitude of wave A? The amplitude can be found as the greatest displacement a wave has occurred. This example is a transverse wave, and amplitude was covered in the previous lesson, 4.1 oscillation. So if you want to cover back on that, go back to the previous video and then come back in here. So, in order to find the amplitude, we have to find our greatest displacement from equilibrium position. We say that the equilibrium position is the black line here. Wave A is denoted by the dark black line here. To find the amplitude, we have to find the greatest displacement that has occurred. So this can be in the positive direction or the negative direction. So it can be either the distance from here to here or this distance right here. If we look at our units, the displacement is in millimeters. And here it says 5. So we know that the amplitude, which we can denote as x naught, is equal to 5 millimeters. Or if you want to rewrite that, you can write that as 5 times 10 to the negative third. Next, wave A has a frequency of 9 Hertz. What is the speed of wave A? So let's first write down our given, which is frequency is equal to 9 Hertz. We want to find the speed, and we're recalling the equation of speed of a wave that is equal to C is equal to the frequency times by the wavelength. The wavelength of this wave A we can find because this is the displacement distance graph. So the distance between 2 points that are in phase will be our wavelength. So usually we can find this from different, as we said before, a point that are in phase, such as a crest to a crest or a trout to a trout. But in this scenario, we only have one crest and one trout. So we just have to find it from 2 points that are in phase. This point is the starting of the oscillation, and this is where it completes one full cycle. So these 2 points are also in phase. So the distance from here to there is also the wavelength of the wave. That means that the wavelength of the wave is equal to 8 centimeters. When doing that, we can say that 8 times by 9, because speed of wave is frequency times by wavelength, 9 times 8 equals 72. So that means that our speed of our wave is going to equal 72 centimeters per second. We can box that up because that is the answer. Finally, we're going to want to find what is the frequency of wave B. This is wave B denoted by the dotted symbol. We know that the speed of the wave, which is not going to change, is going to be 72 centimeters per second. This is going to remain constant. So this means only that there's going to be a change in the wavelength. So we're going to want to find the wavelength of this wave, which once again we can find from 2 points that are in phase. So here we do have 2 trouts and 2 crests. So if we measure this distance, we get somewhere around 3.8 to 4.0 centimeters, because the unit now is times 10 to the negative second. So we can say somewhere in between, which is 3.9 centimeters. If we rewrite our equation, c is equal to f times wavelength, we can also write it as c equals to wavelength, the speed of the wave divided by the wavelength is also equal to our frequency. So if we want to find the frequency of wave B, we can divide 72 by 3.8, so our speed of our wave, by our wavelength, to give us a final answer of 18 Hertz. And that is going to be the frequency, of wave B.